This video will introduce the concept of the classification of matter. This is introductory concept in general chemistry, the first semester. So we're going to start with all matter at the top. And the first division is between substances that are pure substances and substances that are mixtures of at least two pure substances. Next, we have the next division, and that is mixtures. If we look on the right-hand side here, mixtures can be subdivided into heterogeneous mixtures or homogeneous mixtures. So a heterogeneous mixture is, I'm going to show you an example of that in a few minutes, sort of a picture of that. But an example of a heterogeneous mixture would be something like concrete. Concrete, if you look at it, you can see very obvious different pieces that are different parts of the mixture, right? So you might have some rocks mixed in with some cement. So concrete is a good example of a heterogeneous mixture. There are a lot of other ones too. If you mix sand and water and you mix it together, it's very clearly a separate mixture, right? As opposed to a homogeneous mixture, if you dissolve sodium chloride in water, then that is homogeneous. You can't identify the different parts of the mixture. It looks like one. Every piece is exactly the same. If you looked at the top of the mixture, it looks just like the middle of the mixture, it looks like the bottom of the mixture. But if you took a piece of concrete and you zoomed in on one part of the concrete, you might be looking at a white rock, whereas if you looked at a different part of the concrete, you might be looking at a piece of gray substance, right? So let's move on. Pure substances can be divided into elements, which would be found on the periodic table, and compounds, which are comprised of at least two elements. And so there are different kinds of compounds that we're going to look at later, but a compound has at least two elements in it. The two different major types of compounds are molecular compounds, or molecules, and ionic compounds, or salts. And we're going to look at both of those. We're going to learn a little bit later how to distinguish those two from each other. And we're going to talk about this a little bit more in a few minutes, but mixtures can be purified by physical separation. So we're going to look at some examples of that, but you can purify a mixture and separate it into its pure components doing what is called a physical separation. So there are different types of physical separations. It might be filtration, or you might boil. If you had salt water, you might boil the water to remove the water from the salt. All sorts of examples of that. On the other hand, if you want to separate a compound into its elements, then you have to chemically separate those. And so what that means is that you have to actually perform a chemical reaction. So for example, if you have water, H2O, and you want to convert that into hydrogen and oxygen, you have to actually chemically separate those. It's called electrolysis. We're going to talk a lot more about that second semester. So this is a very similar flow chart, just like the one I just drew, but this looks nicer because it doesn't have my terrible handwriting. It's typed. So I wanted to talk a little bit more. I wanted to show you some pictures of the different, mixtures versus pure substances. In half a second, you can see that the on the left-hand side, it shows you how you would decide, right? If something has uniform properties, then it would be not a heterogeneous mixture. If in the bottom, the chemically decomposable, if it is not, it's an element, and if it can be chemically decomposed, it's a compound. The chemical decomposition you can see on this flow chart between compounds and elements is chemical separation. So that would require a chemical reaction to, for example, convert H2O into oxygen and hydrogen. At the top, I want to talk a little bit more about physical separations when we separate a mixture into its pure components. So as an example, we have a mixture shown in A, the box at the top left. This is a mixture of 4 different solids. One of them is sand, one is iron, one is sugar, and the other one is gold. And so if you if you look, you can see that it is a heterogeneous mixture, because if you zoom in with a magnifying glass, you can see the sugar is this sort of clearish white crystals, and you can see some shiny gold kind of on the left-hand side, and then the darker substances, the darkest substance there is iron filings, and then there's also some sand or silica in there as well. So if we wanted to separate this and form the separate components that you see in B on the right-hand side, then what we need to do is do a physical separation that takes advantage of differences in the properties of these materials. So if we think about that, the most significant difference and probably the easiest first step in this separation would be to separate the iron. So if you think about what's different about iron than the other three substances, iron is ferromagnetic. It is attracted to a magnet. This is a very common first step in recycling, or if you ever go to a dump or something, then you can see that there is a big magnet that pulls out the recyclable metals, and so that's always generally a first step in these recycling systems. So that would be an easy first step. The next probably easy step would try to separate out the sugar. Sugar is soluble in water, which means that if you add water to the sample of sugar and sand and gold, then you could dissolve the sugar, and then on the bottom you could filter that sugar solution through, and then the solid gold and silica, the sand, would stay inside the filter paper in the funnel, and the sugar water would flow through. Now gold and sand are both very different in density, and then their particle sizes are different. So you might use a mesh sieve or something to separate the two solids that are remaining. They also have different densities, and so that's a very common way of separating them, is to add a liquid that has different densities that would allow one of them to float if it's less dense, and then the other one would sink. That's also very commonly used in recycling. Now if we wanted to separate the sugar, you can see the sugar water that's kind of at the bottom. We added water to it. Obviously if we wanted to remove that water, we could do that. We would have to evaporate it away, right? So if we wanted to recover the sugar completely, we would have to evaporate the water. Now this is a picture of some what are called salterns, where we want to produce salt or sodium chloride, and you can see that there are a lot of times out in nature what we do is we just evaporate the water away, and that from salt water, and then we can recover the sodium chloride left behind. Different colors indicate different concentrations based on things that have been. And then we already made reference to this density issue. Gold is denser than sand, and so you can get it to sort of sink to the bottom. That's sort of the idea of panning for gold, right? That gold sinks and other things might not be and might not sink as easily. Now, distillation is something that we're not going to do this semester, but you will do this next year when you take organic chemistry. Distillation relies on differences in boiling points of two different liquids. And so if you wanted to distill, separate two mixed liquids from each other from a homogeneous mixture, then what you see on the left is the boiling mixture. And then what happens is the one with the lower boiling point will boil, and the vapor will travel up into the arm of that what's called a condenser, and then it travels down the condenser arm as a gas. But cold water from like a tap flows into the condenser, and it forms this sort of surrounding coldness which causes the vapor to condense back into a liquid. But because you boiled it away from the other one, it's not entirely pure, but it's mostly a pure liquid. And then you can recover the what's called distillate in the flask at the bottom, and it is much purer than it was before. Another example of a physical separation is something that we're going to do this semester, and that's called chromatography. Chromatography is a very general idea where we have what's called a mobile phase and a stationary phase. The mobile phase moves and the stationary phase stays still or stationary. There are different kinds of chromatography. The one that is shown here on the upper left is called paper chromatography. And the way that works is that, for example, there is a pen and somebody marked with the pen a black ink spot. And then if that paper is placed into a beaker or container of water, then what happens is the water will travel up the paper, and we're going to talk about why it travels up the paper later, but as it travels up the paper, what it does is it dissolves the ink. It has to be, well, in this case, water won't dissolve Sharpie, but let's assume that this is a soluble black ink pen that's soluble in water, like a washable Crayola marker. Or, you know, if it's Sharpie, maybe you don't use water. Maybe you use acetone or ethanol or isopropanol. Something will dissolve that Sharpie for sure, right? So you choose your mobile phase, which is the liquid. It's going to travel up the paper. It's going to move. It's going to dissolve the ink. And then what it does is it continues to travel, and some of the inks are going to be more attracted to the paper. Other inks are going to be more attracted to the water or the mobile phase. So what you see on the right with the Sharpie, right, that's a finished chromatogram, there's a blue spot at the bottom followed by a green spot and a red spot and an orange spot and a yellow spot. What you can deduce from that, from this example, is that the blue spot must be much more attracted to the paper or the stationary phase. The yellow spot is much more attracted to the water, the liquid, or the mobile phase, and that's why it travels the furthest up the paper. So what's important here is that you've separated the 5 different inks from each other, and you realize that the black ink is really a mixture of 5 different colored inks. The bottom right-hand side is another type of chromatography that's called column chromatography. And in this case, it's very similar, but instead of using paper, you use sort of this white powder, and you put the mixture at the top instead of at the bottom, and then it travels down the column, and you can see that what was once a purple mixture separates into a red and a blue mixture, a red and blue components, and they travel down the column at different speeds. And so the red component is much more interacting more favorably with the mobile phase, which is why it travels quickly with the mobile phase as it travels down by gravity. And the blue component is sort of more attracted to the stationary phase, which is inside the column, and it doesn't travel as quickly. But what's important is that you have separated them. We go back and we look at elements versus compounds. Elements would be present on the periodic table of elements, which we're going to talk more about soon. And compounds would be a combination of 2 or more of these elements. And so we're going to look at examples of those now, elements versus compounds. The very bottom are some examples of elements. We have some monatomic elements like helium. Monatomic means they're single atom. We have some elements that prefer to exist in a diatomic form like O2. And some are polyatomic, so there might be multiple atoms attached to each other, S8. But all 3 of these at the bottom are all elements because there's only one element present. The top, however, contains compounds which are comprised of 2 or more elements attached to each other. Now, all of the compounds at the top are molecules. They are molecular compounds attached with covalent bonds. We're going to compare those later to ionic compounds, which are also considered compounds. They're just attached differently. And we're gonna discuss more. We have a whole separate unit on how you will identify molecular versus ionic compounds. Now, last but not least, I wanted to get a little bit into physical and chemical properties, just so that people understand what those are. Physical properties are pretty much any way that you would describe something based on the way it looks. Temperature, color, melting point, quantity, solubility, density, all of those things are physical properties. Chemical properties, the examples listed here, rusting, combustion, tarnishing, hardening, they generally always involve a chemical reaction. That's why they're called chemical properties. So a chemical property that's not listed here might be how reactive something is to oxygen, or how reactive it is when you add water to it. And so reactivity tends to be a chemical property. So chemical properties just require a chemical reaction. So we have an example next of how to distinguish. Okay, so the following are all properties of chlorine. Classify them as physical or chemical. Chlorine combines with sodium to form table salt. That is a reaction, which means that is a chemical property. Color is green. Colors are physical properties. So I'm going to put a C on the first one, we're going to put a P on the second one. That's a physical property. Density is also a physical property. Doesn't require a reaction. Freezing point of chlorine is negative 101 degrees Celsius. That is also a physical property, so no chemical reaction is occurring. The following are all properties of oxygen. Iron will rust in the presence of oxygen. That is a chemical reaction, rusting of iron, so that is a chemical property. Oxygen combines with carbon. I can already tell you it's a chemical property because it's combining with another element, which is a reaction, so that's chemical. Oxygen is a colorless, odorless gas. That's a combination of three different physical properties, colorless, odorless, and it's a gas. There's no reaction involved in that, defining that as physical. When coal is burned in oxygen, the process is called combustion. So burned in oxygen, that sort of implies that there's a chemical reaction going on. We're going to talk more about combustion reactions later, but that is definitely a chemical reaction. Now this last question refers to intensive or extensive properties. An intensive property is something that is inherent in the substance. It is something that doesn't depend on how much substance you have present. So for example, the temperature of something would be intensive, right? So if you have a pool full of water and you measure the temperature, let's say it's 25 degrees Celsius, and then you pull out a small amount of that water and you measure the temperature again, it's still going to be 25 degrees Celsius. However, the amount of heat that's contained in that pool is going to depend on how much you have. And so you might have, you know, I don't know, 3,000 joules of heat stored in the pool, but if you pull out just a small quantity of that, it won't be 3,000 joules, it'll only be 30 joules, right? So the amount of heat stored inside that water is going to be extensive because it depends on how much you have. So other examples of extensive properties would be, you know, anything that is going to increase as the amount increases. So mass is a good example. Other intensive properties would be things like density, where it doesn't matter how much you have, the density is still the same. Okay, so let's go through and do these. The first one, a chemical reaction requires 3 grams of oxygen. 3 grams, that is an extensive property because the mass will go up as the quantity goes up, right? If you double the quantity of oxygen, it's going to weigh 6 grams. Solid copper hydroxide is blue. That is an intensive property. It'll still be blue regardless of how much you have. The density of helium is 1.64 times 10 to the minus 4 grams per cubic centimeter. That is an intensive property because if you had a larger volume of helium, it would still have the same density, right? It would have a different mass though. The melting point of aluminum metal is 933 Kelvin. That is an intensive property. Melting point is intensive. The color of a cobalt compound, that's intensive. The diameter of a soap bubble, that will depend on how much you have, right? The bigger volume of, the more soap you have, the bigger the diameter could be. The mass of a diamond is definitely extensive. It depends on how much diamond is present. The volume of a solution is extensive. If you double the volume, then the volume is going to be greater, right?